otherwise speak about Properads and homological differential operators related to surfaces. Yeah, you
in the previous talk was about the operads, and the Properads are some kind of generalization of this concept. And unfortunately, I don't have enough time to talk about their relation to ideal infinity algebra, so I will talk about some another aspect, and that's how to interpret the algebra over the cover complexes, some homological differential operators. So the first, what are the Properads? So the operad has several inputs and one output, but this time we have also several outputs. And as with the operads, we want to have some sigma action on the inputs, and we also want to have some sigma action on the outputs. So we have the sigma bimoidal, the left and right actions, and we also want to have the composition maps, which will this time take several outputs and several inputs, B and A, and glue them together. So we want to have some kind of differential gradient vector spaces, and the components are indexed by this set C and D of how many inputs and outputs is of the result. There are several axioms like sigma, bimodal, equivariance, and associativity. And basically, if you want to have some idea how it looks, is that you take something like this, you glue the B and A sets, and you get new component, new element of some different component. So obviously, it's good to have some additional grading by genus or Euler characteristic, which is non-negative grading. And in our cases, we will consider only the stable components, which means that the Euler characteristic is greater than 0. The basic example is the closed Frobenius properad, which you maybe already met, and that's that you take each component is just one-dimensional vector space. So the sigma action is trivial, the differential is trivial, and the composition maps do not depend on the sets itself, they depend on the sizes of the sets. And if you want to have some idea, geometrically, it's like two-dimensional surfaces where you have some punctures, and you say that some of them are inputs, some of them are outputs, and you glue them together. And the genus here is really the geometrical genus as you would think as a first. There's also the open Frobenius properad where you have boundaries, and the punctures are on the boundaries. And in that case, unfortunately, the genus is not the geometrical genus. So the additivity of Euler characteristic is not there satisfied. The example which we will use in the next is the endomorphism properad, where each component is given as a homomorphisms from this symbol stands for the unordered tensor product. If you take the general set, you don't have some ordering. And this time you have some non-trivial differential, which is given from the differential of the original vector space. And what you are considering is that when you want to say what is the algebra over properad, it's the same as with the algebra over operad, is that you just make the evaluation of the properad in this endomorphism properad, satisfying some conditions with compatibility with the sigma actions and how it works with the composition. And now just briefly, what is the Kovar complex? In our setting, it's a factor from Properads to Properads, and basically what you get is the suspended dual, the free Properad over the suspended dual of the Properad. And you can think about it as some graphs which are oriented. You have no directed loops and some other conditions, and each of these graphs is decorated by some element, where this part stands for V1 up to Vn are the inner vertices. You suspend them so you get the element formally of the degree n, and this P1 up to Pn are the elements of the dual vector space of the original Properad P. So you get the graphs decorated by this. The composition this time is just, you grafted these graphs together according to orientation of the edges, and you have this time non-trivial differential. This part is given from the original differential from the original Properad, and this is just basically dual of the original composition maps. And now, if you want to think about the algebra over the Kovar complex, you can take it as in the original definition, or you have there is another way that you look on the degree 1 linear maps from the dual of the vector spaces to the endomorphism proper, as you would expect, and they have to satisfy these conditions, like the sigma structure is given by the inverses, and there is some compatibility with the differential. And you can continue. You can take these equivariant maps, sigma equivariant maps, and there is isomorphism to the space of invariance. And so you basically can think about the algebra over the cover complex as some element L from this space, where you take all the components together, and this element satisfies some master equation, that the differential is simply given as this, and the composition is rather technical, but it's straightforward. You just transfer the composition from the original covariant complex, algebra over covariant complex. And the invariants are, in this case, isomorphic with coinvariants. So you can also take this component by component, then together these spaces are also isomorphic. And you again can transfer the differential and the composition maps. And now if you will consider that the sets of the inputs and outputs are not empty, and we choose some ordering of them, we can introduce something called positional derivation. That you take the derivation according to Aj on these elements. You jump to the kth position, and you compare if it's the same with the j you were making the partial derivation. And then you can make several of them. And if you look on the set of the coinvariants, then you basically can interpret them as the positional derivation where the inputs of the properad are acting on the outputs of the other part. Like when you have that composition maps, then the inputs are a partial derivation acting on the outputs. So that's how you can interpret this structure. And that.
Right. Thank you very much indeed. Again, there's time for questions. Quick questions. It's hard to ask questions after such a yeah, please.
Yeah, I'm not an expert and I'm not claiming I understood anything, but as far as I understood, there's some viewing of surfaces and you have some mass equation. Yeah. This looks pretty much like closed string field theory, right? Is there some relation to the PV mass equation you have there?
Yes.
It's like
that's basically where you have a closed Frobenius and open Frobenius properad, because it's related to this. But
okay.
Yeah.
All right, yeah. Thank you again. Before everybody rushes off for dinner, we do want to have a session that is announced as a discussion session in the schedule, which is meant to actually be that discussion. Let me just introduce briefly what the idea is. So the title of this meeting is High Structures in M Theory, and so what's the point? On the one hand, as you all know, string theory is an incomplete theory. M theory is still an open question, even though we all got used maybe to saying the word all the time. It's actually an open problem. And over the years, many people in the room too have